more than 98 is not possible here.
I'm denying, sir. I'm denying actually.
Okay.
I'm waiting for sir and director sir and vice principal sir.
It's a very good response given by our students as well as all other another students also.
I'm putting, please.
Okay. You can continue, sir. Please continue.
Sir, actually, students are putting this thing. I'll need to move the down first, please.
What you should do is you should do auto. No, but you can do auto entry. Then you can. Okay.
Yes.
Yes, that's problem.
Here, director sir is there. Good afternoon, sir.
Hi.
Yes,
Okay,
good
Mr.
afternoon. Yes, good afternoon to all of you.
Sir, with your permission, should we start?
Yeah. It's already 1 o'clock. Let us start.
Sure. Thank you, sir. I hope my screen is visible to all.
Yes.
Yes, it is visible.
Once. So, a very good afternoon to one and all present for this technical webinar based on capacitor and power factor improvement by our today's expert, Mr. Hemant Joshi sir. So, I am the host for this particular technical webinar about our expert, today's expert, Mr. Hemant Joshi sir. He has done his master from IIT Bombay in 1981. He has his BE from Shivaji University. Properly, sir, belongs to basically from Maharashtra origin and from Nagpur. Nagpur, yes, sir. Sir, I'm from there only, sir.
Oh, okay, good.
And as a brief about sir, as I have told you, sir, sir, kindly give me your introduction. Actually, if we are going for LinkedIn, sir has a huge basically intro part. But sir told me that no, you just put this 2 to 3 points, not more than that. So, sir, this is as per your point. So, sir is basically electrical engineer. Basically, he has been in Australia with 35 years of consulting experience in various countries. I hope in all countries, more or less, in New Zealand, Australia, Indonesia, China. And sir has been basically providing his expertise to the power utilities substation infrastructure such as airport, port breeze, water pumping station, prisons, universities, buildings. So I believe as far as the knowledge is concerned of Hemant sir, it is in all domain. If your name and we are there for as far as electrical engineering is concerned. So sir, I'd like to inform you about our college as well as department. So, sir, our college established in 1983, started basically computer. We have basically started with 3 branch in 1983, civil, mechanical, and electronics. And then in 1990, we have come up with the computer. Then 2001, IT. 2004, we have a PG course in mechanical engineering. 2010, MBA and PG courses in civil engineering. 2011, we have PG course in electronics and computer engineering. Sir, for your kind information, we have our PhD course as well in mechanical. And meanwhile, as far as electrical engineering is concerned, we have started in 2017, sir. So we are new as compared to our branches is concerned branches. About department, sir, it is affiliated to Savitribai Phule Pune University, starting 2017-18 year. Basically, intake is 60 plus 3. And as far as admission status is concerned, sir, we have SY BTech, which is an autonomous. It is 81, T 70, and 57. Faculty strength, sir, 1 faculty completed PhD, 2 are pursuing. And we have faculties with ME and MTech. So this is what faculty experience. As far as faculty achievement concerns, sir, we have basically 2 awards and recognition in terms of paper presentation. We have completed online courses 35, journal publications, international journal 12 and national 2, conference publication 10, national conference 9, STTP with all department we have 45, as far as workshop and industry trainings 11, webinar 90, MOS we have done 3, recently we have gone in this semester one. Product development, we have sir one, and we have with the movement as with IIT Bombay, where you have done your MTech basically with Professor Chetan Solanki sir. He has movement is Swaraj Energy Foundation, so we are forwarding it also. Sir, and professional societies, we have ESA, Gate Club, IST, IEEE Student Chapter, Student Council, just to motivate us to bring the laureates in that. Certification programs, so we have SAP Global Certification, and the institute is the center of this. And we have gone with the PTL as well. Online courses certificate, basically, we have SY BTech 148, workshop 140, publication basically 11. This is all about students, sir. Industry internship 15, mentorship program 20, university rank holders, we have 2. Being a new department as well, we are putting our all efforts. Inter-institute participation, we have 5. Participation in project competition, hybrid vehicle competition, M Baja and Bija. These are the project competition which students are taking up. Sports achievement, we have 5, including national level selection. Cultural development, yes sir, we have basically going. And the highlight is basically our entrepreneurs, sir. Basically, being a 2017-18 students only, 18 department, we have 3 entrepreneurs till now, in which
yes, just a minute. You make full screen.
Okay, sir. Okay, is it
Okay, fine. It's now full screen.
so? In this, sir, basically our SY and T third year students are taking much more basically participation as they are having autonomy and they are full-fledged freedom to take what they want. So second year student, we have Swami Rachavan. He's basically digital marketers, whereas third year student Harpreet Singh, he's putting his e-bike basically on an venture. And we have Shubham from SY BTech, who is going for manufacturing of LEDs. So this is what with the highlights, sir. So now I request Hemant Joshi sir, director sir, to welcome our today expert, Mr. Hemant Joshi sir. Director sir.
Joshi sir.
Hello, hi.
Yeah, hi, good afternoon. I don't know for you it is good afternoon or good morning.
Evening.
Good evening. Okay, fine.
Yeah.
Okay, so I welcome you to Sanjeevani, as well as we are all thankful to you for accepting our invitation and doing it happen. So I heard that you have done your bachelor's degree from Shivaji University. Which college?
Karad.
Karad, Government College, Karad.
Yeah, Government College Karad. Yeah. My
Yeah.
father was posted there at that time. So I joined Karad.
Yes, fine. Okay, sir. Now you can take over and let us
Okay,
continue.
sure.
And the subject which you have chosen for today's session, I think it is very important because most of the power which we generate, because of improper power factor, we lose a lot of power.
Yep.
So a power saved is nothing but is a power generated also.
Of
So
course.
it's a very good topic.
Yep.
So, sir, now you can take over.
Yep.
And now
Thank
let
you.
us move on.
All right. Thanks for the introduction, and it's my pleasure to be with you today. Okay, now, I have to share the screen. Where is it? Okay. Have you passed on the host to me? Okay, let me see. No.
So now I hope you can share their screen.
Okay. Not yet. Oh, no, it's still you are the host.
Now I've changed the settings.
Okay, no, it is still showing that you are presenting.
Yes, Pandey, you stop your presentation, then only you can do
Okay,
it.
let me see. Okay,
Yes,
now, okay, wait a minute. Yeah, wait a minute. Still, okay, yep, here now. Yep, it's working. All right, yeah. All right.
Joshi sir, your screen is visible now.
Okay, yep. Okay, so, okay, wait a second. Okay, yep. Now it's full screen, and can everyone hear me clear and loud?
Yeah, you are clearly
Okay.
audible, sir, as
Okay.
well as your screen is also visible.
Okay, okay, sure. We'll start then. Okay. Namaste and good morning, everyone. My name is Hemant Joshi. As you have been told, I live in Brisbane, Australia. Most of my life I worked in Australia and New Zealand. My Indian experience is only a few years. I left in 1990, India. Today I will talk about capacitors and power factor improvement. Many electrical engineers don't understand these fundamentals and hence make mistakes in work. All right, we start with application. Capacitors are used for power factor improvement, most common application, which we are going to talk about. Voltage improvement in utility, power board, HV and EHV system. Okay, and we don't use for voltage improvement in industry, only by the power boards. Harmonic filtering in industrial utility, that is FACTS and electric traction systems. Harmonic filtering system is mostly a bullshit. Capacitors were also used for motor starting to maintain voltage during start and then cut off in industrial system, but rare nowadays. So in old days, when I was a young engineer, some places they used to, in the industry, they used to use capacitor for starting to maintain the voltage and then switch it off once the motor has started. Nobody's doing that nowadays. Okay. Application. Continue. Super or ultra capacitors are used in electric cars and trains during acceleration because it can provide large power in short amount of time, which a battery cannot. But not a must. The car train can accelerate using battery also. But we are not talking about that. Plus various other applications. In this lecture, we will talk about application of capacitors for power factor improvement only. All right. So let us look at construction, type by construction. Two types of construction: dry type and oil impregnated type. Dry type, also called as metallized polypropylene (MPP), and which is very popular because the polypropylene film used as a dielectric. The film is coated on one side with zinc or aluminum, which acts as electrodes. More sensitive to temperature. Generally, low voltage units are available in dry type. Oil impregnated, oil is used for cooling and as dielectric. High voltage units are oil impregnated only. LV capacitors. It is not possible for a purchaser to ask or select between dry or oil impregnated because some manufacturers offer dry type, others offer oil impregnated. Okay, so you don't have a choice. The choice is purely based on what the manufacturer can offer and the price. So you just go by price. That's it. Okay, but don't worry about whether it's a dry type or oil impregnated. Somebody may tell you that oil are good, dry is not, and all this kind of thing. Don't worry. Dry is very, very, very popular in LV. Therefore, the purchaser cannot dictate purchaser cannot dictate the construction type for LV capacitor. So we cannot dictate we want oil or dry. Enclosure. The enclosure of a capacitor unit is either metallic or non-metallic, depending upon the manufacturer. Don't bother which type it is, okay? It doesn't matter. Metallic enclosures have an earthing terminal using which the enclosure must be earthed. Each unit is provided with an overpressure device. Once this device acts, the unit can no more be used and must be replaced by a new unit. It is a mechanical fuse connected to the top core of the unit. The power supply to the unit passes through it. The overpressure opens the cover, thereby disconnecting the fuse, this mechanical fuse, and hence the power to the unit. Life. Capacitor have a life of 10 to 15 years. You are lucky to get 15. All right. You all know this. Q is 3V square divided by XC, where Q is the capacitor kVAR capacity, V voltage across capacitor in kV, XC is the capacitive reactance per phase in ohms, which is 1 divided by 2 pi FC. You have learned that in your engineering electrical. But remember, because engineers learn this and then forget when they start working. That means the kVAR generated is directly proportional to the square of the applied voltage. For example, in delta connection, the applied voltage is 400 volt, while in a star connection, it is 230 volt. You all know this, correct? Therefore, delta connected unit will give more kVAR than star connected unit for the same system voltage and capacitance per phase. Okay, so that's why preferably the units are connected in delta. Okay, to get more kVAR in the same unit. Therefore, the low voltage units are available in delta connected only. These are three-phase units with three-phase bushings terminals, one terminal for each phase. As mentioned before, these are connected inside the enclosure in delta connection. Therefore, a neutral is not required in the power circuit of low voltage capacitors. Neutral is required only for control supply in the power factor correction system. Okay. Most engineers specify full size neutral for power supply to the capacitors. And then we don't know, if the contractor doesn't know where to terminate it. So please don't do that mistake. Okay, you can run 2.5 mm square, like even if the 100 kVAR capacitor or whatever the bank size is, you can run a 2.5 mm square neutral that is required only for control supply. So this is how it looks. 1, 2, 3 terminals. Okay. This is how the connection is. Okay. This is the voltage across each capacitor unit. The standard voltages are 380, 400, 415, 440, 480, 525, 600, 660, and 690 volt. The standard ratings are 2.5 to 100 kVAR. 100 kVAR is the maximum single unit you can get in LV. The required capacity is achieved by connecting number of units in parallel. Okay, so if you connect 2 units, for example, if 400 kVAR capacity is required, then either 8 times 50 kVAR units or 4 times 100 kVAR units in parallel. Okay. The construction is IP42. I hope you know what is ingress protection. I don't know. I hope you have studied that, but I don't have time now to explain. I got another lecture for that. So the construction is IP42, which it can be installed indoor only. Outdoor IP55 minimum. High voltage capacitors. These are available in single and three-phase units. Single phase units have either 1 plus 1 dead or 2 live bushing. I will show you the picture shortly. Three-phase units have 3 bushings, star or delta connected 3-phase units. Okay. This can be installed either indoors or outdoors, provided correct IP rating is specified. That is IP42 for indoors, IP55 for outdoors. Most manufacturers offer IP55 only. Okay, so that means the same unit can be installed indoor or outdoor. The 3-phase units are either delta or star connected, that is both types are available. The standard unit rated voltages are 3.3, 6.6, 11, 17.5 or 21 kV. Okay, this is the bank. I'm talking about the bank now. Okay, which consists of various units. The standard unit ratings are from 50 to 1000 kVAR. Okay. The problem is not every manufacturer will offer delta and star connected. Not every manufacturer will offer full voltage and kVAR range. Okay, so like for example, manufacturer A may offer only up to 11 kV, other may offer up to full range 21. Somebody will offer up to 500, somebody will offer up to 5000. If 22 kV or higher voltage bank is required, then appropriate number of single phase units will have to be connected in series to get required voltage, and then groups in parallel to require kVAR. Okay, so series parallel combination. So this is how it looks. 3 bushings. Okay, RYB, 3 phase. Okay, so this is the 3-phase one. This is single phase. So single phase, you got 2 options: 1 live, 1 dead, or 2 live. So if you are using for delta connection, then you need this. Okay, if you need star connection, you use this. Internal fuse. The unit is made up of several series and parallel elements. I will show you a photo in a second. Internal fuse is provided for each element inside the enclosure of the unit. If one fuse blows, then it will be lost and the unit can continue to operate. External fuse. This is normal fuse outside the unit. Internal fuse is preferable. Most manufacturers offer both options in LV and HV. Okay, so this is how it looks, internal fuse. So you can see these are each element and there is a fuse for each element. So if this fuse blows, only that element is gone, the capacitor unit keeps functioning. Okay. And externally fuse. So the fuse will the voltage switchboard for this capacitor. All right. Temperature category. Capacitors are very sensitive to temperature, so you have to be very, very careful while selecting. okay, and fail if outside the temperature limits. For 4 temperature categories, A, B, C, D. A is 40 degrees centigrade, B 45, C 50, D 55. These are maximum permissible temperatures for each category. The minimum permissible temperatures are 5, -5, -25, -40, -50 degrees Celsius. The capacitor is specified by category and minimum permissible temperature. For example, -25D. So what it means is this capacitor can operate between -25 to 55 plus 55 degrees centigrade. Okay. So depending on where the capacitor is being installed, you have to select the proper category. If the room temperature is going to be 50, you go for C. Room temperature is going, you are confident it is 40, then go for A. If you are not sure at all, go for D. When disconnected from the discharge, when disconnected from the power supply, capacitors retain the charge which you have which must be discharged before working on a capacitor. Be very careful while you are working on an inductor or capacitor. You need to discharge them because they retain the charge and you can get a shock. Therefore, discharge resistances are provided at terminals of each unit. So I'll show you this. This is the discharge resistance here between the two terminals. So as soon as capacitor is disconnected, it discharges through that. The resistance are to discharge the unit to 75 volt as per IEC and 50 volt as per Indian standard. In 1 minute for capacitors up to 650 volt, that is low voltage. In 5 minutes for high voltage capacitor, that is above 650 volt. I don't know why Indians have different standard like 50 volt. No idea. Inrush current. When switched on, the capacitor acts like a short circuit, and which you must have learned in the first subject of electrical engineering. Or the first, whatever. So when switched on, the capacitor acts like a short circuit and draws a large transient current up to 100 times its rated current, generally for up to 4 cycles, which reduces slowly to steady state current, okay, means rated current. This inrush current is drawn from 2 sources. The electrical system it is connected to and other capacitors in parallel. So if you have got 4 into 100 kVAr units and three units are already operating and you switch in the 4th unit, not only the system, the 4th unit will draw inrush current from the electrical system plus these 3 units in parallel. Okay, so the more units in parallel and the last units you switch in, more inrush current. Therefore, a series reactor is provided in series with each unit to reduce the inrush current. Generally, a 4% series reactance is enough, but the harmonics criteria requires a minimum 7% reactance, and therefore a 7% reactance is provided. Overcurrent and overvoltage. Capacitors are rated for 1.3 times the rated current continuous. This is a requirement of the standard IEC, and same Indian standard also. So this is a requirement of international standard. All in this. This is to account. We are more sort of conversant with IEC because in Australia and New Zealand we work with our standards have been converted to IEC now. This is to account for higher than the rated current due to various reasons such as harmonic currents, tolerance on capacitance, etc. So you have learned that everything has a tolerance, plus or minus 10%, 5%. So the capacitance value. So if with the minus, it will draw more current. The maximum voltage at the terminals of capacitor is a combination of following. Due to Ferranti effect, you must have learned that the voltage at the terminals of the capacitor is more than the system voltage. If the series reactor is 7%, then this can be up to 7% higher than the system voltage. Okay. So if it's if the system is 400 volt, 7% is 28. So the capacitor voltage can be up to 428 volts, okay, due to the Ferranti effect. Due to the power utility voltage fluctuation by regulation, this is generally plus 5%. Minus, you don't have to worry. So because we are not talking about the higher side. So the power company always says that, okay, our voltage will not be 400, it will be 400 plus or minus 5%. So if you put 5%, so then it means 20. So now you have got a series reactor, which is 7%, which gives 28 volt. Power utility is saying, oh, my voltage can be 5% more, which is 20 volt. So the total voltage can be now 448 volt. Okay. So you have to, when you are ordering capacitor, you have to consider that. Therefore, the capacitor must be rated to withstand 5 plus 7 equal to 12% of over voltage continuously. Okay. Hence, the capacitor voltage rating is selected 1.12 times rated system voltage. Correct. 7% here and 5% here. For example, if the rated system voltage is 400 volt, then the rated capacitor voltage must be 1.12 times 400 equal to 448. 440 is the nearest, which is quite safe to use, not a problem. Because it's very, very rare to have a utility voltage go plus 5%. If you're lucky. In India, it will be on the minus side. Okay. And when in the light load period, capacitor won't be in the circuit, so not a problem. Do not specify a 480 or 525 volt for a 400 volt system. The unit will give less than rated kVAR because kVAR is directly proportional to the voltage square. Okay. So if you are connecting the same 100 kVAR to the 480 volt, it will give less kVAR. Okay, not 100. So, remember the equation. Okay, resonance and harmonics. Contrary to the popular belief, or so just let me go back to this. Okay, so you have ordered 440 volt capacitor. If you have ordered 440 volt capacitor, then it will give 100% at back. If you put higher, okay. So if you give order a 480 volt for that and use in 400 volt system, it will give less. Okay, so system is 400. Okay, so whatever you are put, so that will generate the voltage across capacitor. Okay, so if you are using 480 volt capacitor in a 400 volt system, the kVAR output will be less. It will give 100% at 480 volt. Okay, at 400 volt it will be less. So at 440 volt it will be less than 100. That's how it works. Resonance and harmonics. Contrary to the popular belief of 99.99% of electrical engineers, capacitors do not produce harmonics. In my life, I have met 99.99% electrical engineers who think capacitors produce harmonic. They do not. It is a static equipment, and it doesn't produce harmonics. Okay. The capacitive reactance XC is equal to 1 over twice pi FC, where C is the capacitance. Higher the harmonics, that is the frequency, lower the capacitive reactance. The inductive reactance XL equal to twice pi 2 pi FL. L is the inductance. Higher the harmonic, that is this frequency here, higher the inductive reactance to the system to which the capacitors are connected. At one of the harmonics frequency, the capacitive reactance may become equal to or close to the system inductive reactance. The net reactance will then be 0 or low, XL minus XC. Okay, if XL, XC are very close, the net reactance is very, very small. Okay, that means then V divided by that, with the current will be very large. Therefore, a series reactor is that reactance I'm talking here about is the reactance of the transformer. It is supplying the low voltage switchboard and then the capacitor. Okay. Therefore, a series reactor is provided in series with each unit to avoid this situation. Okay, so you basically shift it. Okay, you avoid that situation to come at all. Generally, a series reactor is 7% of the capacitive reactance at system frequency. If the capacitor system is whole as one unit, that is no steps, then only one series reactor is provided. That means a bank has 4 units, then 4 three-phase reactors required. So for each unit, you need one series reactor, independent, separate. Same principle applies to average capacitor bank. The triple N harmonics don't enter individual phase capacitors. I hope you know triple N harmonics, 3rd, 9th, like that. Okay, in that order. Okay. So they don't enter capacitors because they connected in delta. So remember, triple N harmonics, they cannot get out of a delta and they cannot come inside a delta. Okay, this is a fundamental thing. Very few engineers know. Okay. 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 I'll show you. Okay, 30. Let me show you this. Okay. So this is the delta. Okay. So triple N cannot come because they're like zero sequence current. Okay. And same, if it is here, they will continue circulating here. They cannot get out. So if you have a delta connected capacitor bank, you don't have to worry about triple N harmonics. Okay. Therefore, low voltage capacitor units and delta connected high voltage capacitor units have to worry about non-triple N harmonics. That is 5, 7, 11, etc. Okay. So we don't worry. So if you have delta connection, don't worry about triple N, 3rd, 9, etc. Okay. Oh, you have to worry only about 5, 7, 11, etc. Hence, the reactor is tuned for fifth harmonics, okay, because fifth is the largest. Star-connected high voltage capacitors are affected by tripling harmonics, and hence better not to choose for power factor correction. So here is an example. Imagine a 500 kVAR power factor improvement capacitor is connected to the low voltage side of a 500 kVA transformer, which has a 4% impedance through a 7% series reactor. So the 7% reactor is between the transformer and the capacitor 100 kVAR unit. Impedance of the cable is negligible, don't bother. The transformer inductive reactance in ohms equals, you know this formula, so I won't go through that, 0.0128 ohms. The reactance of the series reactor in ohms is 0.07 into 1.6 kV square upon MVA. Okay, straightforward. Okay, 0.112 ohms. I hope you know all these equations. Okay, otherwise go and check your books. The total inductive reactance of, so you cannot, whatever you are studying in the university, in your institute, don't forget, you will be applying in practice. Okay. The total inductive reactance of the system equal to transformer reactance plus series reactor impedance 0.0128 plus 0.0128 plus 0.112 equal to 0.1248, say 0.125 ohms. The reactance of the capacitor bank in ohms is equal to kV square upon MVA. For 100 kVAR unit, the reactance is 1.6 ohms. Okay, that's why we had here 1.6 times 0.7, sorry. The above value of impedance is at 50 Hertz. Third, 9 etc. tripling harmonic current don't affect power factor correction capacitors because they are connected in delta. A fifth harmonic frequency, at fifth harmonic frequency, the impedance will be as follows. System impedance will be 5 times 0.125 equal to 0.625 ohms. Capacitor bank impedance 1.6 divided by 5, 0.32 ohms. Okay, so we are safe here, no harmonics and no resonance. Okay, so you can see that because we have added the series reactance, the harmonic situation has been the resonance situation has been avoided. Okay. All right, so that was the basics of capacitance. Now we talk about power factor improvement. Why we need to improve the power factor? Power factor improvement is required only if the electricity tariff demands for the consumer. Therefore, this application is only for consumers. Okay, power utility, they don't need to improve their power factor. Okay, it's a consumer. So the consumer has to improve the power factor so that automatically power utility power factor is improved. Okay, so the onus is on the consumer, not the power company. Okay, and if the consumer doesn't, then the power company will penalize it. Okay, so now there was a time a lot of countries didn't have this requirement. Like for example, New Zealand didn't have this requirement until 1995. You'll be surprised. Now, I don't think there is a country in the world which doesn't have this requirement that a consumer must maintain a power factor above 0.95. Electricity retailer's tariff requires to maintain certain minimum average power factor over the period of each billing cycle. Okay, remember, not month billing cycle, which is usually 0.95. Okay, billing cycle is the cycle when the consumer is billed. Okay, so the cycle that may not be first of month to 31st of month, may not be that. It depends on the retailer. If the retailer let me start from 5th of that month to the 4th of next month or something like that. Okay, so it depends. Like when you are given the connection, so if your connection start on the say 10th of November 2020, then your billing cycle will start from 10th of November. Okay, like that. The retailer calculates the average power factor over each billing cycle, not calendar month, by a pre-disclosed method in the tariff contract. Okay, so every retailer has its own formula how to calculate this average power factor. So I cannot tell you what is the general formula. Okay, so but they have to tell this method to the consumer. Okay, they cannot keep it a secret. Okay, so if you are a consumer, you can ask, what is your formula to calculate average power factor? Okay, it is calculated by the retailer using the kilowatt and kVA measured over a measuring cycle, usually half an hour, every day using the revenue meter. So they measure this every half an hour and they say, okay, so many reading we take and then average out and all kind of things. Okay, but basically they measure kVA every half an hour. The algorithm to calculate average power factor using the data varies from one retailer to the other. It is not simply Pythagoras theorem as taught in the textbooks. Okay, so it depends on the retailer how he calculates it. If the power factor is below the stipulated value, then a penalty is charged at the rate specified in the tariff. Electricity retailers' tariffs for individual residential consumers are not required to maintain minimum power factor. So residential consumers are exempted. Farmers may be exempted. Like you have to check, depend on the retailer. He says following customers, some type of consumers are exempt, and these are the ones who have to maintain. Okay. Power factor of loads. Okay. So the loads cause the power factor of that system for the installation. The different load, resistive loads such as resistance heaters, unity power factor. IT servers, power factor varies between 0.0 to 1 lakh, could go lead as well. Okay, therefore important to check. There was a time until few years ago, IT systems power factor used to be poor, like 0.7 lakh. Nowadays, IT servers have the opposite problem. Okay, they come at 0.98 lakh or sometimes 0.98 lead. Okay, so IT systems are no more a problem generally. Okay, as far as power factor is concerned. UPS power factor varies between 0.9 to 0.9 lakh. Okay, but this again depends on the IT equipment it is supplying. Okay, so nowadays this is also not a problem. Motors operate below 0.95 power factor, lower the motor rating, kilowatt, lower the power factor. Okay. Roughly, I would say any motor about from 100 kilowatt and above will definitely have 0.92 or better power factor. Some light fittings lamps are power factor corrected to 0.95, others are not. Therefore, check before selecting. Arc furnace 0.5 to 0.7 lakh. Arc furnace is very, very horrible. Very good. How to improve the power factor? By the consumer providing automatic power factor correction system, APFCS, in the plant building electrical system. So very, very simple. This system consists of capacitors which generate reactive power at leading power factor, which cancels some of the load lagging power factor, reactive power. Easy to install if the installation is in the design stage. You can incorporate in the design and do it. Quite difficult or sometimes impossible to provide in the existing system. Each existing installation case needs to be reviewed on its own merit, whether you can install or not. Some installation you just cannot. The difficulties are when the switchboard have spare breakers, the switch room has spare space to install the power factor correction panel, etc. How to improve the power factor? Continue. The rating capacity of the APFCS is in kVAR. Its operation is automatic. The required power factor is set on its controller. I will show you the controller. The controller in the AFCS switches the required capacitors in or out to maintain the safe power factor. So the controller senses the power factor, and depending on how it will switch in the additional capacitors, or it will switch out. Okay, if the power factor is way higher, it will switch out. If it is just there, it will see. It looks like it's going down. It will switch in. Criteria. The criteria for existing installation are totally avoid the power factor penalty by maintaining all the time the power factor above the minimum value stipulated by the retailer. Common sense. For example, if the retailer has stipulated minimum 0.95 power factor, then design power factor must be 0.97 to have a safety margin. If you set at 0.95, you could be in trouble. Okay, so set it at higher. Cost of the power factor correction should be recovered within 5 years. Return on investment. So there is a standard formula for return on investment. You put the numbers in that and you see whether you can get in 5 years. Otherwise, it's not really worthwhile. You may have to check whether better to pay the penalty. But it's a balance between this. Okay. The new installation, no need to worry about. Okay. For new installation, the return on investment exercise is not carried out because the cost of the power factor correction is small compared to the total project cost. So when we are doing designing the new installation, we don't do this investment on return calculation. On existing, you may do it or you may not do it. Your choice is the client's choice. All right. High voltage versus low voltage power factor correction system. The choice between low and high voltage correction system arises only for high voltage customer. If the customer is low voltage, obviously it is going to be low voltage power factor correction system. If the customer is a low voltage customer, receives power at low voltage, then obviously low voltage system is the only option. For a high voltage customer with all the load in the low voltage system, That means all equipment is at low voltage. The low voltage power factor correction is a better option because of low cost. Okay, so for example, you are receiving power at high voltage because the power company says your total demand is more than certain kVA, so we are going to give you HV supply. Then what happens is then you get HV supply and you step down, and then all your load is at low voltage. So you have step down transformer and you supply. So in this case, you are better off to put in the low voltage system. Okay. The other advantage, it is then also reduces the capacity required of the transformer, because the transformer doesn't have to carry all the reactive power of the load. So closer to the load, better. Okay. But it doesn't work out practical. But don't reduce the transformer capacity, keep it as an extra design margin. And if the customer has all high voltage equipment, then obviously high voltage correction system is the only option. But such a system is rare. If the customer has mix of high and low voltage equipment, then maybe both type of APSC. Okay. Usually high voltage motors will have more than 0.9 power factor or more even. Okay. So having to put high voltage power factor correction system is a very, very rare situation. Okay. Not certain. Only you will encounter that in a very large industry, especially like steel, metallurgical, mining, or that kind of big industry, like which have huge load demand. Okay, not otherwise. A detailed, most of the light industry, medium industry, commercial buildings is low voltage. Okay, so it's very rare to put high voltage. A detailed technical feasibility and cost benefit analysis is required in such a case. Okay, so in the last case, you have to work out whether it is worthwhile to put in the high voltage, because it's very expensive. Usually, a large industry will have such a system. Not very rare. In my whole life, I think I have come across only once high voltage, but it was a smelt mine. Okay. High voltage APFC is many times expensive and requires substantially more space as compared to the low voltage system. The reason is it involves high voltage breakers and contactors, which are expensive and take a lot of space. For example, a 400 kVA low voltage power factor correction system may cost around $40,000. Whereas high voltage system will cost around, like same capacity will cost around $150,000, so almost 4 times. It is very rare to require a high voltage system, only for large industries, I told you. Okay. Conventional versus active power factor correction system. Two types of power factor correction systems are available in low and high voltage. Conventional contactor controlled, also called as passive system. Thyristor controlled, also called as active system. The active system is expensive as compared to the passive system, but gives no extra advantage. Okay, so the manufacturer, they try to fool the engineers, and engineers get easily fooled. This is this is state of the art modern system. The problem I have with engineers nowadays is that young and old all, that they are after modern and high tech technology without thinking, is it really required? If it is not required, why you waste money if it's not giving the advantage? So for example, whether you go conventional or thyristor control, the objective is to maintain power factor. Whichever system you go, it will maintain the power factor at what level you want. So why pay more money if you are achieving that by a cheaper solution? Okay, so there's no extra benefit, nothing. It's only high-tech technology, they will say, nothing else. Just because load is, and they will say, oh, if your load is fluctuating, you use that. No, okay, it is not true. Just because load is fluctuating doesn't mean active system being fast will correct it. No, it won't correct it. Okay, it will do the same, correction will be same as a conventional system. Remember, it is not instantaneous power factor, but average over billing period. So you got a half an hour billing period. Okay, so you have to correct that. Okay, so not in seconds. Okay, so they will say, oh, this will correct it in seconds. So you don't, no need. Okay. Location. If a high voltage power factor correction system is selected, then it is connected to the high voltage switch port. For example, if the 6, then the APFC is provided in the 6.6 kV system and connected to the 6.6 kV motor control center. For arc furnace, it is connected to the same bus bar as the arc furnace. If low voltage APFC is selected, then it is provided in the low voltage system. The standard industry practice is to provide at each low voltage main switchboard connected to a transformer. So every transformer is connected to a main low voltage switchboard. So you connect to you provide the system in that switchboard. Okay. If the building has only one main switchboard, then you need to provide only at one main board. If it has more than one, if it has more than one transformer, if suppose it has 4 transformer, then you have to provide the system at each of the 4 main switch boards. This is the cheapest and best option. Don't waste time in any other option. Calculation of amount required. The scientific way is to calculate the total load of which the power factor is to be corrected in kW and kVA, and then using these values calculate average power factor kW by kVA. Using average power factor, calculate capacity divided on the capacitor band. So this is what you have been told in the books. Okay. So this is the original kVR and this is the capacitor one. So this is the final. So it will get you the required power factor. Okay. So this is the method in the books. Okay. In practice, you cannot use this method. I'll tell you why. But in real life, it is not possible to get power factor of all loads, and hence such a scientific calculation is almost impossible to do. For low voltage APFC, the rule of thumb is 40% of the transformer kVA. So if your transformer is 1000 kVA, then 400 kVA capacity power factor correction system is adequate and safe to provide. Okay, because you can scientifically you have to get each and every type of load and then its power factor and the kW and kVA, but this information is not available in practice. Okay, so you cannot do. So you can do this calculation in 1 minute and you are absolutely safe. Okay. As a design engineer, better to be safe, because if the client is hit with penalty due to wrong calculation, then he will recover it from the design engineer's company. Actually, 30% is also good enough in most cases, but I will never take a chance because of this. Okay, because if by chance it is not adequate, then the client will say, okay, I have been penalized for bad power factor, Mr. Design Engineer, you pay me. Don't take risk. Number of steps. Depending upon the controller, either 6 or 8, like some manufacturers offer 6, some offer 8. Okay. There are various ways to select step size. Option 1, all same. That is, if you want 6 into 50, 300. Option 2, combination of different size, 25, 25, 50, 50, 50, 100. So its total is 300. Not possible to give any firm guideline which one to use. Okay, so you just see and decide. Okay, usually most cases this equal one is good enough. All right. Sorry, it's not very clear, but this is how it looks like. All right. So this is the automatic power factor correction unit in the panel. So you have got, here they have shown 12 steps, but it's not like that. Okay. So generally each capacitor will have a fuse. Actually, there will be an isolator, then fuse, and then contactor, the series reactor, and the capacitor. The contactors which is in and out. And this is your power factor automatic controller, power factor controller. Okay, it is sensing the current and voltage of the load. So thereby it determines the power factor. And then depending on how many kVA are required, it will switch the contactor in and out. Okay. So very, very simple system. There's no rocket science. Okay. So that's what I'm still telling you, that you need 3 conductors for this, okay, R, Y, B. But for, okay, the neutral you need only for this controller, okay, and so a small neutral is enough. Okay. This is the voltage. Actually, you don't need the voltage transformer. You can straight away connect the fuse, the power factor controller. You can, through the fuse, you can connect to the live conductor. You need only one. Okay, so you can connect to the R phase or Y phase or B phase. Okay, so this is a single phase. Sorry. This is phase-to-phase supply. Okay, so it will sense phase-to-phase and then current. Okay, because it's sensing the voltage. Okay. And there is a fan provided to keep the capacity, the temperature within limit. Not a very good idea, because if the fan fails, the capacitor will cook and die. So ask for a capacitor without capacitor unit, which will work without fan. Okay. So we got voltage supply from here, current supply from here. And then it senses the power factor and straightforward. And this is the group isolator. Okay. Okay. You can have instead of isolator and fuse, you can have MCCB also. Okay. The contactor is special with insertion resistance. This okay. Remember, this contactor is capacitor duty. There are various type of category of contactors. This is a capacitor category. So what it means, it has a resistance. This resistance is switched in first to reduce the inrush current, contactor cannot withstand more than 6 times its rated current. Okay, so even though your capacitor can withstand a bit more, contactor cannot. And then main contacts close, bypassing it. Okay, so first the resistance comes into the circuit, it reduces the current, and the main contacts then close, and then the contactor gets the rated current. The series reactor is a must to avoid resonance at any frequency from system frequency to harmonic frequency. Okay, so when you are checking a part of this drawing, okay, from the vendor, from the supplier, make sure this contactor is that capacitor duty type. That means it has insertion resistance. Some manufacturers are stupid. They will provide you ordinary contactor, which is used for switching light circuit or motor. It is not good enough. Okay, it will burn. Mostly they will supply us the contactor which is used for switching on the lights. All right, this is how it looks. These are the KVR bank. This is the series reactor, and this is a contactor, fuse. Okay, so as I told you can have MCCB instead of fuse and etc. This is not a good design because he hasn't provided the isolator. Okay, never ever do that. Always have an isolator, because if you have to work on the capacitor, you can isolate it. Okay, pulling out fuse is not a good idea. All right. This is the power factor controller, okay, and then you press the button and set the power factor on it, okay. Maintenance. Capacitors are sensitive to temperature, and hence the room must be ventilated to maintain the temperature below the rated temperature of the capacitor. Remember category? So whatever category, so if it's a 40, then the room temperature must be below 40. That means say around 35. Apart from examining contactors for carbonization of contacts and checking capacitors every year, there is no maintenance. The capacitor can be checked by a simple multimeter using DC voltage on it. The capacitor should show open circuit, zero frequency. If not, then must be replaced. Very simple, straightforward. Common mistakes by 99% engineers. The control system shall automatically disconnect the power factor capacitor while the building industrial plant is operating on the standby generators. I am sick and tired of explaining engineers. You don't need that. So engineers think that the generator cannot handle this power factor correction capacitors. No, it can. What happens is when the power goes off, all the capacitors drop out. Okay, and the generator comes on line, and then as the load is switched in, the capacitor bank starts switching in the capacitor units. Okay, so the generator is not saying all. So that load is already. So the generator is saying a good load power factor. It is not saying a leading power factor. Okay, of the capacitor. So the generator is operating at whatever the load power factor is, which will be about 0.96, 0.95. Okay, so what the problem? Okay, but generally what happens is generally the generator supply and the main supply is different breaker. The capacitor correction, the power factor sensing is provided on the mains breaker. Okay, so when the generator comes in, the power factor correction unit doesn't come in picture at all. Okay, it just doesn't stream. If only the switch supply is there, if the generator is stepping up the supply and then going through the same breaker, then only it will be sensed. Okay, so in most of the cases, when the generator supply comes in, the power factor the system is automatically disconnected. Okay, you don't have to do anything, and you can run the power factor correction capacitors on generator. There is not a problem because the load is always there, and the capacitor load power factor together is a good power factor. The thing is that these people learn somewhere, and that okay, the generators cannot work on the leading power factor. Yes, it is true, but they are not going to see that power factor at all. They are not feeding only the capacitor bank. Okay, in that case, it is different. A generator cannot do more than 40% of its kVA capacity as a leading kVAR. Okay, so for example, 1000 kVA generator will not be able to supply more than 400 kVAR leading power factor load. Okay, so but it doesn't happen here. Okay, it is supplying the normal load. Effect of solar plant not considered. So if you are having a solar plant, then what happens is that is set at unity, okay, power factor, okay, to keep the inverter size down. Okay, so it means then the grid has to supply rest of power, and which will lower your power factor. So if you are having a solar power plant, you will need bigger size capacitor bank than the normal one. Okay. Because, for example, you have a 100 kilowatt solar plant. Okay, that means grid is not okay. So that 100 kilowatt is coming at unit power factor. Okay, and then that means the power from the grid is reduced by, so the total power is say 500 kilowatt. Okay, so 100 kilowatt coming from here, 400 from the grid. Then the 400 from the grid has to be at higher power factor. Okay, so compensate for this. Okay, and so that's why you need solar power. This you need a bigger capacity bank. Okay. Conclusion. HV power factor correction is very expensive, should be provided if only must. Provide power factor correction only at the switchboard MCC connected transformer because it is most economical. Okay, don't provide at the motor or distribution board. Very, very expensive and maintenance nightmare. The load profile of commercial building and most industries is pretty flat during training hours. Therefore, a central power factor correction system such as above switchboards MCC is adequate in most cases. Most of the load profile is very, very flat. Okay, if you see a shopping mall or if you see industry, it's very, very clear that from 9 o'clock or 10 o'clock it goes up and stays like that till 6. Suppose shopping mall, say 10 or 9 it go up, let's say maybe 10 o'clock, and then it stays like that till about 9 p.m. in the night. Okay. Industry also same. Whatever is trading hours, it runs full flat. Okay, nobody is the load is not going up, jumping up and down as many people think now. Okay, so there is no need. You provide at one main board, that's enough. Motors 100 kilowatt and above are unlikely to require power factor correction. Therefore, check whether really required. VSD control motors are unlikely to require power factor correction because VSD takes care of it. Okay. Don't bother about claims such as voltage improvement and reduction in losses if provided at other locations and close to individual loads. These advantages are not tangible, that is, cannot be converted into monetary savings. So somebody tells you, okay, you provided the motor, and that way your cables have to carry less kVAR and less current, and you are saving in I square R, that is energy loss. You cannot calculate that tangibly. Okay, so don't worry. Provided the main switchboard, that's the most economic solution. Okay, so all these things, it is all good in the books, but not in the practical industry. That is all from me. You're most welcome to ask questions. You can also email me questions on this subject or any other electrical engineering subject on hemantjedu@gmail.com. I'll be happy to answer. And I would like to say a few words after the Q&A session. Over to you. Okay, wait a minute. I will go to chat box.
Yes, anyone, participants? Mostly I feel that students should ask the question because as sir has...
Yeah, anybody.
Yes. Sir has definitely has given all sorts of basically what is basic to what we should do being an engineer, what you not to do. Yeah. So, yes, one we have
here. Everyone is talking about PF improvement of solar, hydro and all, but very less people are talking about